7.2 video 4 for example number 3. This one looks very similar to the first example that we covered. Again, it's going to have the exact same kind of setup. Now in the previous example we used algebraic as our u and our dv as exponential or trigonometric. So in this case, since the algebraic and the exponential are back, we're going to try and let u equal our algebraic again, and we're going to try and let our dv be our exponential one more time. There seems to be a pattern to these problems, and again, the more you do them, the more you practice them, the easier they'll get, the more you'll realize what you're going to let each piece be, so that you don't have to actually think about it later on. Don't forget, again, your formula is the integral of u dv equals uv minus the integral of v du. So with this particular formula and this setup, we're going to go ahead and follow the rules for what we did before. U is going to be our algebraic equation. Our dv is going to be our exponential equation with the dx. Don't forget that everything multiplied together with u and v must create this entire integral. So then I have to identify what du is, which is 2x dx. And v, when I integrate that, is nothing more than e to the x. So I've done all the grunt work, and now I'm just going to plug everything in. So this is equal to, again, uv. U is x squared, v is e to the x. So I'm going to have x squared e to the x minus the integral, again, because that's what the formula is, minus the integral of v du. So v is e to the x, du is 2x dx. So the statement that comes up next is I've taken this integral, I've integrated a part of it, but here is no longer as simple as the first example that we were looking at, or the second example that we were looking at. This is now a function, e to the x, multiplied by another function, 2x. One more time, I have an integral of something that is now what this should have followed from. Again, this is nothing more than another integration by parts. Okay, again, when I try to integrate the secondary piece, the intent is that it should be simpler than the first step. This was x squared e to the x. This is technically more simple. It's a linear function times exponential instead of a quadratic function times an exponential. But that does mean that we can't integrate this as it is. We're going to have to do an integration by parts again. So again, keep in mind up here, these u's and v's have nothing to do with the actual integral. They are nothing more than placeholders. So I'm going to go ahead and hide those two pieces, and I'm going to follow the rules again. I'm going to let u equal something, I'm going to let dv equal something, and hopefully this will be able to simplify down. U we let equal to the algebraic function last time, so I'm going to follow suit with that. Don't ever use integration by parts twice, where you let u be the algebraic function, you let your dv be the exponential function, and then you swap them so that my u is now exponential and my dv is my algebraic, because you're going to do nothing more than backtrack to the original problem. Again, don't swap the way you let those functions exist in the u and dv pieces. So from here, again, I'm only working on that integral. I'm going to let u be 2x, so my du is then 2dx. I'm going to let dv be my e to the x dx, so my v is just e to the x. With that done, I'm going to carry down all the pieces. Now keep in mind, this is equal to x squared e to the x minus this entire integral, which I'm going to put nice big brackets around everything that's supposed to go inside that integral, because I want to make sure that that subtraction sign gets distributed to everything here. Keep in mind, we are using this integral now with this rule again. So now I'm going to have uv minus the integral of v du. Again, they're just placeholders. So with that being said, this integral right here is u times v, so 2x e to the x, minus the integral of v e to the x du, 2dx. Now there's a couple of things that we could have done differently in this problem. For instance, we could have said, hey, this is a constant multiplied by everything inside here. We can pull that constant out and put it with that negative, in which case there'd be a 2 out here. But then this 2 here wouldn't be there, and this 2 here wouldn't be here, and we'd still have to go ahead and distribute that 2 at the end anyways. So I just went ahead and left it in there. So now I have this piece sitting outside. I'm going to distribute this negative right here to both those two pieces, and end up with x squared e to the x minus 2x e to the x plus the integral of e to the x times 2, which I'm going to go ahead and slap outside, dx. Again, that 2 came from this 2 right here. So with this done, all I have to do is evaluate this integral. again, integration by parts got this part out. Second integration by parts got this part out. Now I've just got to integrate this simple integral, which will provide me with x squared e to the x minus 2x e to the x plus 2 e to the x. Don't forget, we have to tack on that plus c when there's no bounds, and we've integrated our last piece for integration by parts. And that's the final result for that one. So one last question to leave you with a thought for is, what if instead I gave you this? Or I just kept adding on powers and gave you something like this. You should be able to start seeing a pattern. If you look at the previous example that dealt with e to the x, you'll notice that we started with a singular x e to the x and devolved down into just e to the x and then plus c. In this case, we went ahead and had x squared, and it became 2x and then just 2. This should follow a very similar pattern if I work with this one. What I would recommend is this is going to take 3 integration by parts. Again, 3 methods of int by parts. You should do that, okay, follow through with all 3 of them, and then there are a couple of examples in terms of where you can find where that answer is and see if you've got it all right. The most difficult part you're going to have with this is honestly the constant values, making sure you've carried them through accurately. But that finishes that problem and that concept.